So today we're going to talk about three different kinds of complement system. And the first one we're going to talk about is the classical. And the classical uses C1q-R2S2. And it has to have an antibody complex to be able to have a complement reaction. Now this classical is a part of the adaptive immune response. And that is because it has to use antibodies. Furthermore, so once you have the antigen antibody complex bind, and then you have your C1q R2S2 bind, you're going to have your R2 and your S2, which are serine proteases, chop C2 and C4. These are going to further chop into C2A and C2B, C4B, and C4A. In the C2, the C2A is the larger subunit, and the C2B is the smaller subunit. That is a little bit different. Majority of the time, the A subunits are going to be the smaller one, and the B subunits are going to be the larger one. So this C4B and this C2A are going to come together and act as an enzyme, which causes the reaction at the C3 convertase to take the C3 protein and chop that into C3A and C3B. Now these C3A and C3B, C3A is will act as an anaphylotoxin, and C3B will act as opsonine, and it also bind with our C4B2A and act enzymatically at the C5 convertase, and that will cause C5 to break up into C5A and C5B. So let's talk about a few things. So this C2B will generally act as an opsonin. The B subunits will generally act as opsonins, such as the C3B right here, and the C3A will act as an anaphylotoxin. And these will activate histamine release in certain granulocytes, and also activate neutrophils and macrophages to further phagocytize different bacteria, viruses, whatever it may be that it's reacting against. So now we're going back to the C5 convertase. So the C5 breaks up into C5A, and C5A is the most powerful anaphylotoxin. And C5B will then go and hook up with the C6, the C7, and the C8, and this makes a complex, and it's glycoproteins will be able to bind to, let's say, a bacterium surface, and enzymatically further catalyze the process of putting C9s. They act as porins to a degree, and shove these into the membrane of the bacteria. And this does a lot of things. Osmosis occurs, putting water inside the bacterium. ATP synthase is going to be negatively influenced, meaning that the ability for the bacteria to be able to make ATP is going to be drastically changed. Furthermore, the hydrogen ions will be coming in, and you will have the gradient will be destroyed, like I was saying with ATP synthase, and virtually you'll have lysis. A few interesting things is that the C3B also involves chemotaxis, and the C3B will need to be reused. Not necessarily reused in the way that we think, but it's going to be binding to red blood cells, and those red blood cells will take it to the liver to get processed again, because this is a part of the adaptive. It wants to be able to know what worked and why it worked, and also you don't need just to have dead bodies per se laying around. So this C3B will act kind of like a tag to allow these apoptotic bodies to be sent and be kind of cleared out of the body. So C3B is very important, probably the most important out of all of the subunits of complement proteins. Then the lectin binding pathway is very similar to the classical pathway, meaning that a lot of the same, there's homologous structures. So the MBL is the main shaft, and then you have MAFs, which act similarly to the R2S2, but this is going to be mainly looking for PAMPs to be able to bind to. So these structures on different bacteria that kind of are the same, it will be looking for those to be able to activate complement. And it has to have, I failed to mention, but at least 2 antibodies have to bind in the classical, and at least 2 of these carbohydrates have to bind. Furthermore, so it's going to go through the same process of going to the C2 and C4 and cutting at particular places and acting like a protease. And it goes through the same process. The C3 convertase is going to use the same enzyme. C5 convertase is going to use the same enzyme. So now we're going to go to the alternative pathway. So the alternative pathway is able to be stimulated or occur with soluble C3 complement protein. So this C3 is really interesting that this whole pathway can be regulated with the availability of C3 protein. So this C3 will spontaneously hydrolyze, and after it spontaneously hydrolyzes, factor B is going to come in and create C3H2O big B. Now factor D is going to cut B into big B little b and BA. So now you have C3H2O big B little b, and this is going to be the fluid phase C3 convertase. Now that we have this fluid phase C3 convertase, we need to be able to put this on a membrane and make it more usable. So furthermore, you're going to have C3 again, just in the fluid, and this C3 will break up into C3b, and then factor B once again will bind, and you'll have C3b big B. Now factor D, once again, very similar, will break up B into C3b big B little b. A goes off, and now you have an unstable C3 convertase, and this is membrane bound. So it's not really necessarily the best possible, it's not usable. To a degree it is, but it's not necessarily the most usable. So pipertin is going to stabilize this membrane bound C3 convertase. So now we have our pipertin bound to our C3b big B little b, which is our enzyme for the C3 convertase, and that's going to break up our C3 into C3b and C3a. Now the C3b, like we were saying in the classical and lectin, it's going to be really useful. So this C3b is further going to bind to this previous enzyme that was used to cut C3 and create an enzyme that fits just right in the C5 convertase. And these C5 convertases will then give you your MAC. So it's the same process that we saw here, where you have your C5b acting as an anchor with your C6, C7, and C8, and then your C9 putting in those, basically drilling into the membrane of whatever it's going to be attacking. A couple of interesting things, once again, is that to regulate this, you can kind of do a negative, or positive regulation with the availability of pipertin. When it's available, you're going to be able to make a lot of this. Furthermore, the alternative is regulated with the amount of C3 available. I mean, if you don't want to create membrane attack complex, just cut off C3. That's why C3 is very important, and C3b is very important. So going back to this, this is very important in how we are able to detect certain things. I failed to mention once again that this lectin complement pathway is actually a part of the innate immune response, and this is also somewhat of an innate response because there's so many different ways we can use this, right? The C3 alternative pathway to be able to get to certain things. Pipertin, studies have been shown that pipertin can act as kind of a place for C3 to be able to make MAC, to initiate MAC. And it's just one of the better things for, let's say you don't have anything that has characteristics, that you don't have time for the adaptive, you don't have anything that is characteristics of pathogen organisms. You're able to use this and still have a viable way to activate the complement. And that's 3 complement pathways.